exception. You look at this molecule having a double bond, of course, that's what you can see first. So you got to think about the reactions in chapter 8. And then now look at the reagents. Chlorine in chloroforms. The reagent is going to give out what's going to happen. So we don't need to worry about it's going to be SN2, it's going to be SN1, or E2, E1. We're not going to talk about that because these already know. With that, it's going to be a chlorination reaction. At least it narrows things down. But there will be more complication, which is something you need to think about. First of all, this is the chloroform. It's a non-nucleophilic solvent. The solvent doesn't participate in reactions. First thing happen, high electrons, going to get the chlorine, you're going to get the chloride out. This will make the chlorinium ion, right? The bridge ion. You're going to get the chlorine, positively charge it. That's going to pull electron density from the carbon bound to. So these two carbon, this becomes electrophilic, electron deficient. But because of symmetry, each carbon is going to lose about the exact same amount of electron density. So I'm expecting these two carbons are equivalent. So the chloride becomes a nucleophile. That's going to come, makes an attack from the opposite side. So you're going to get this carbon gets chlorine, that carbon gets chlorine. But you need to show the trans relationship. You have to show. If you're using regular solid line, what it means is it could be cis. So you're only going to get the half credit because you just mentioned cis and trans together. When we're expecting only trans. So when the stereochemistry is relevant, you have to show to get the full credit. Just like this. Chlorination reaction is anti-additions. So you need to show us products. We will get chlorine, each carbon, but there is a trans relationship. You can show in the other way, chlorine, this one goes down, that one goes up, this one up, down, but it doesn't matter. It gotta be trans. It has to be trans. In fact, both those two will form together. But you only need to show just one of them. That is kind of a simple one. That's very simple, except the stereochemistry. I just want to show you the stereochemistry also becomes an issue too. This is a question that I think made it very difficult. Doesn't look like it, right? But you see. You have a cyclopentene, of course, methylation here. Double bonds, more substituted side, less substituted side, right? When you see the double bond, not symmetrically substituted, then you gotta be careful. Bromination, probably not, because this gets bromine, that gets bromine. So same thing goes in, so it doesn't really matter. But for other reactions, you need to be careful. But anyway, high electron is going to attack the bromine. I would expect that's the first thing to happen. That's going to make the brominium ion, like we discussed before. Make the bromine positively charged. That's going to make these two carbon electron deficient. Now, you need to think about which carbon is going to be more electron deficient. More substituted one or less substituted one? Which one can help out? Which one can afford to help out? This more substituted carbon can lose more density because of this method can help it out. That doesn't have enough electron density. So the more substituted carbon will get more electron deficient, and that's what is left of bromides going to make an attack. So nucleophilic bromide going to make an attack on the more substituted side. And then this bromine on the less substituted side, that's the one that from the brominium ion. Of course, it's the same molecule, same atom. So you're not going to see the differences, but somehow if you can paint the bromine by like a radioisotope or anything, more substituted side is going to get attacked. That bromine is the one that left out from this reaction. That's it. Nucleophilic bromide is going to be common on the more substituted side. Less substituted side one is going to come from the brominium ion. These two bromine, again, have to be trans, right? All of these things have to be right. Biochemistry, the one we talk about here, which one, and then stereochemistry, those two, all of them has to be right. But this is the same bromine, so term doesn't really matter. What makes things difficult is what if I add a water to that? If I add a water to this whole thing, just same thing, And the waters are not going to be attacked by the double bond because the water is not the electrophile. So even though you add a water double bonds, nothing's going to happen. Bromine is the one that's still in the lead away by making attack first with the pi bond. So these things happen. The thing is now in the solution, not only the bromide left out, you got water. Two nucleophiles present together. And then solvent molecule, you got that solvent molecule is going to be outnumbered the bromide. You got so many solvent molecules there. Even though this is not the most strong nucleophile, it's just outnumbered. So that things can make an attack on the more substituted side because the more substituted side lost the molecular density. Then you're going to get the hydroxyl group sitting on the more substituted position, not the bromide. That makes you got two different things added to the double bond. Bromine goes to the less substituted side, hydroxyl groups go to the more substituted side, and then there are trends. Now, specific biochemistry, specific stereochemistry. To get this answer right, you need to think about aspect of the reactions. Not only the following the mechanism, you need to think about the where it's going to happen in biochemistry, how things going to happen in stereochemistry. So that's why we love this kind of reaction to make a questionable. Carbohydrate reaction, you really want to know. After showing this, I can still make this thing harder. So what other way I can make it harder is adding another nucleophile. Strong nucleophile, really strong nucleophile. The same thing. It's a lot of things mixing together. But the cyanide, never going to get attacked by the pi electrons. Waters, never going to attack by the pi electrons. Only the bromine is going to attack by the pi electrons. This is a mixture of the things. But the first thing happened is the bromine getting attacked by the pi electrons, having the bromine ion prepared. Of course, when you bromine ion prepared in the solution so far, you get the bromide here, you get the water here, but now I'm adding a cyanide as an additional nucleophile. Now the three different nucleophiles competing. Bromide makes an attack, water makes an attack, or really strong cyanide makes an attack. Which one do you think will get the better chance if there are somebody equally present? It's a nucleophilic attack, so strong nucleophile works better. That's something that you learned from the previous chapters. So cyanide, if there's enough cyanides in the solution, then that's going to make an attack and then make this thing happen. So cyanide is going to be added on the more substituted side. So change the product. But the things we talk about in concept, the same thing. If nucleophile makes an attack. You only adding up just a little specks of cyanide, and I would expect that because it needs to outnumber, these bromide and this. And water molecule, many of them there, but they're just make a big, nucleophilic attack. But cyanide is basically it's a heavy punch. A heavyweight champion comes in big and knock here. Even though it's one shot, it's gonna be knocked out. Rather than just basically making a little jab. It takes a lot of jab to make knock something down, but that cyanide is a giant. It comes and make a huge punch, and then things gonna go this way very easy. If you got enough number. The enough number doesn't mean that you need to outnumber every single one of them. It's just enough there. So that can change the outcome of the products. So these reactions are loaded with so many things to consider. That's why we love this question. I'm already warning you. You're gonna get this question for the quiz, you're going to get this question for the test. This one is what you want to know. Anyway, so if you do everything in there together, I'm expecting that as a major reaction, a major product. For the major product, I've been telling you, many things has to be right. Is that you're going to get the bromine added on the less substituted side, nucleophile cyanide in this case, and the more substituted side. And then not only that, you gotta show the trans relationship because of the anti-additions. Any part is wrong, you get deductions. Okay? Maybe I'm warning you too much, but it's gonna be like this. Every single reaction we're gonna see from now on, biochemistry, stereochemistry, every single one of them is right, and there will be 20, 30 reactions coming to you. It's gonna be busy. I'm really making a hundred. But you really want to use your 100 on top of the fancy liquid. Okay. I hope I can find this. This one, I want you to recognize the products of the haloform reaction, right? Halogen is one carbon, hydroxyl is another carbon, and then there are trends. This is a product of the halohydrogen reaction looks like. Halogen the one carbons, hydroxyl the other carbon, right? In order to make this happen, you know you can get this one done by the chlorine ion prepared first, and water makes an attack. But in order to make the chlorine ion, what do you need? You need a lot of double bonds. But here, you don't see a double bond. So can we make a double bond with this? Do you know any reaction to make a double bond with that cyclohexyl chloride? That is an elimination reaction. Like a PB oxide, you make an attack, come in, take these protons, then you got this kicked out, you're going to get double bonds forms. Then you're going to get the halide chlorine, the chlorohydrogen reaction during adding chlorine in water. So this is a kind of a multi-step reaction. You should be able to figure out what you need to make things happening. It's not just one reagent adding it. You need to think about by steps. This one comes first, and that one comes second. You need to number them because we're not mixing everything together. Just like when you want to enjoy the nice pasta, you don't eat the dry pasta and then drinking the boiling water and then soup and the tomato and just jumping up and down. Maybe in the stomach you get the same thing, but it's going to be different experiences, right? So we need to prepare them, and then that's what you need to show. You're going to make the double bond first. The first step, making an elimination reaction. Second step, halohydrogen reaction, right? That's why you need to number them. Now, why we need a T methoxide? Can we do it as methoxide? If you're using a regular methoxide, you may be getting a double bond, only the portion. Some of the methoxide will attack here, you get this SN2 reaction done. So in order to prevent SN2 reaction not happening, you probably want to use the Herky base, right? The things that you learned in chapter 6, you still have to know. So that's why if you didn't get a good score in test 2, you really need to make it up. Because we're going to still need it. So this is kind of the things that you need to, the test is going to have some question like this. You need to figure out what to do. You need to choose a reagent right. In order to make the right choices, you need to know what each one does well. Not only the biochemistry, stereochemistry, all different issues. So something like that is what you need to prepare for. And these questions are the same thing. See here, hydroxyl groups here, chlorine groups there, and then there are trends. That is the features of the chlorohydrogen reaction we just talked about. But you really need to be careful. Waters on more substituted side, chlorine on the less substituted side, right? That's a mark of different products. If the waters are here, chlorine's there, you cannot make it with the chlorohydrogen reaction. You have to make it some other way. The first thing you need to recognize what is the product you need to make it so you can figure out what reaction that you use. So the chlorohydrogen reactions, how they looks like, the nucleophilic bound, which is a water, on the more substituted side, chlorine on the less substituted side, and there must be trends. If you see anything wrong, they both cis or the water this way, chlorine go the other way, they're not the products of the chlorohydrogen reaction. You gotta recognize it. And this is you already know what this. The only thing that you need to think about is this one is done by the double bonds. That part's exactly the same as what we talked about. But the thing is, how are you going to make the double bonds with this? Should we put it with like what PB oxide as like if we did? PB oxide, gonna pick out the hydrogen and then kick out the hydroxyl groups, make a double bond. So this is something that you still have to remember the whole stuff. This is not going to happen because the hydroxide is a bad leaving group. You cannot kick the hydroxide out. Only way you can do it by adding acid in this case. You're going to make this hydroxide as a water. Water takes out, you're going to get a carbocation. The carbocation, then you can make a proton goes an E1 reaction, and you can make that out.